Okay, good afternoon, everyone. My name is Sean Daisel. I'm from SAEON Elwandle based in Quebec, and welcome to the October SAEON Seminar. It's just about 2 minutes after 2, and I don't see any further additions to our attendance. So I'm going to kick off proceedings. We will shortly start with introductions and then have the presentation by Dr. Human, and then that will be followed by questions from the attendees. You're welcome to put your hand up and ask questions. Otherwise, type your question in the text box if you want, through the talk if you want, and we will address those after the talk. So thanks all for attending. I would appreciate it if everyone can just keep their mics off throughout the talk, please. It is my pleasure today to introduce my colleague, Dr. Lucienne, biogeochemist at SAEON Elwandle Coastal Node. Dr. Human received his PhD early 2014 from the Nelson Mandela University under mentorship of Dr. Gavin Snow, Professor Janine Adams, and Professor Guy Bate for study on the contribution of submerged macrophytes and macroalgae to nutrient cycling in a great bucket estuary near Mossel Bay. Since then, Dr. Human held several lecturing and fellowship positions under Professor Adams at Nelson Mandela University before joining SAEON Elwandle in 2017 as biogeochemist. Under his leadership, Dr. Human literally advanced the biogeochemistry platform from a single instrument, a water analyzer back then, to several dedicated laboratories and high-end instrumentation, now able to analyze an array of materials and variables, ranging from microplastics to metals. But his true passion remains being in the field, where he works alongside colleagues and friends from around the world. I have it on good authority that the real reason people are lining up to work with Dr. Human is not because of his good sense of humor, but because he makes the best curry dish you will ever have on field trips. So with that, today, Dr. Human will direct our attention to the Knysna Estuary to give us a water and sediment biogeochemistry perspective on the water quality of the system. And over to you, Lucienne.
Thanks, Sean. Thanks for that introduction. Was a bit long, which means I'm getting old. And anyway, thanks a lot. Yes, today I'll talk about the water quality of the Knysna Estuary. And just to give you an outline, excuse me, is it moving? It seems to be frozen. Is it moving on your side?
Not yet on this side, Lucienne, but we will wait.
Okay. There we go. Okay. So just to give you an outline, this talk will be split into two parts. The first part of this talk will is really about the reason why we started working in Knysna Estuary. We were invited there by the late Professor Brian Allenson because of a green tide that occurred in the estuary, and it's the first time in South Africa that a green tide of this proportion was present. It was almost comparable to one that would happen in a European type system. And then the second part of the talk revolves around what we wanting to find out what's happening in the greater part of the system. Both these articles were published. One was in the first one, South African Journal of Botany, and the other one in the African Journal of Aquatic Sciences. So an introduction to the Knysna Estuary. Knysna Estuary is an estuarine bay. It's one of 5 types, although there's been a reclassification of estuaries in the country. There are now 8 types. But going on the old definition from Alan Whitfield, there are 5 types of estuaries in the country. Knysna is an estuarine bay along with Richards Bay. Then we have estuarine lakes like Lake St. Lucia, permanently open estuaries such as the Gantus, estuarine river mouths, like the Caimans, and then temporary open closed systems like the Great Bruck, and there are probably more temperate closed systems in South Africa compared to the other types. And Knysna is actually, out of all the systems in the country, over 200 and odd systems, estuaries in the country along the coast, it's ranked #1 in terms of out of all the systems. And this is based mostly on its biodiversity importance. So it scores very high in terms of its biodiversity for fish, birds, plants, and invertebrates. And then its botanical importance, it's ranked first out of 30 warm temperate systems in the country, and third overall in the country, in South Africa. So overall, a very important system. And this is what the Knysna Estuary looks like from Google Earth. We can divide the system into 3 parts. The bigger estuary, you've got the lower bay. Is there a laser pointer here? Can you? Oh no, I don't want that. Excuse me. Sean, is there a laser?
Lucienne, even if you use your there we go. We can see the laser pointer.
All right. Thanks a lot. So the system can be divided into 3 regions: the lower bay, the middle lagoon, which is from the railway bridge to the N2 bridge, the national road, and then the true estuarine character, where there's actually mixing with fresh water. So we've got fresh water from the river and the sea coming in, and where they mix, you have different types of salinity gradients, ranging from fresh, which is 0 parts per thousand, to saline 35 parts per thousand. So this section from the N2 bridge up to the Charlesford Weir is actually considered the true estuary. And then we've got another region in the estuary which was classified in 2003 by Switzer, and his work, he did some work on the Ashmead Channel, and this is where the green tide actually settled, and will be the focus of the first part of this this presentation. So normally when we do our LTAR surveys, we go along the main channel and collect physical chemical parameters and nutrients from the main channel, and we also do this around Ashmead. So in regards to the first study, a bloom of Ulva lactuca covered the lower reaches of the Knysna, and here we have some pictures in the slide. You can see how abundant it was. And normally filamentous algae are involved in green tide, such as Enteromorpha and Cladophora, but in this case it was also Ulva. And this is globally considered a sign of eutrophication. So what is eutrophication? Just a quick definition. It's an oversupply of nutrients to the water, to any water body, whether it be a river, a lake, the sea, or estuaries. And this can often result in negative impacts, for example, red tides, green tides, hypoxia, and eventually even fish kills. So normally when a fish kill happens, it draws a lot of public attention, but the cause of that fish kill is only a symptom of what's actually happening in the bigger picture. So you got to get rid of the source of that, and that's you need to reduce the amount of, or the concentration of nutrients coming into a system. So these are some of the pictures that Professor Allinson sent us, which really sparked or started off this journey, and very intense algal blooms. And this, what was interesting was that the people on Thiessen Island and the communities around Knysna were saying there's a lot of toilet paper laying on the marshes, and they were starting to give sandbox some trouble and blaming the wastewater treatment works for all the loo paper on the marshes. And it turned out that it wasn't actually loo paper, it was just decaying and rotting algae. So as the algae started to decompose, it started to have all these white spots on the marsh. So our aims here was to figure out what was happening, and we were going to measure the nutrients in the water column around Ashmead. Also measure the isotopes, the nitrogen isotopes in the macrophyte material in order to trace the different sources of nitrogen being discharged into Ashmead. So we wanted to see what was the actual source of nitrogen, and stable isotopes is one way to do this. Determine the flux of nutrients between the sediment, so the underlying sediment, what's coming out of the sediment, using benthic chambers. Determine the effect of the macroalgal bloom on the salt marsh, as well as the seagrass, Zostera capensis, which I'll only talk about the impact on Zostera in this presentation. Then we also determine the storage of nitrogen and phosphorus, as well as metals in the macroalgae, to evaluate if it's suitable to be used as compost. These are just the methods. So we use normal collection methods to collect the water in the water column around Ashmead. These are the benthic chamber deployments over here. And so what we basically have is a chamber. This tubing allows us to withdraw the water for nutrients, and water is replaced by ambient water. Whatever is taken out is replaced, and very low volumes are taken out so that we don't change the conditions in the system too much. This is done over a 24-hour cycle, so we get a whole picture of the cycling. The next thing we did, we used a flame spectrometer to measure the metals in the macrophytes. Okay. This is just a picture of Ashmead, and to give you an idea of the hydrodynamics. So we've got the main channel coming in this way. So from the sea, the heads is here. The tide pushes in. It pushes up around this arm and also under the bridge around the top arm. And what it does, it meets there, and that's almost like where it reaches equilibrium and it pushes back again. So we collected samples all around Ashmead at 7 sites, and this is the data I will talk about now. So this is the oxygen on the y-axis, and then our different sites. So site 1 would be at the bridge. I'm sorry, I should have showed you the different sites in this diagram. Site 1 would be around this part. Site 2 here. Site 3 is close to the wastewater treatment plant outlet, something I forgot to mention. Over here, we've got the Knysna wastewater treatment plant, and it discharges wastewater, treated wastewater, and sometimes when the treatment plant fails, it's untreated and it's discharged into this through the small channel here, the Bongani outlet, into Ashmead, and that's where our site 3 is, just opposite that. Site 4 is located close to the Thiessen Island outlet, and site 4, 5, and 6, 7 is around closer to the end of Ashmead. So here we see the oxygen is very well oxygenated in around site 1 at the bridge, and then very well oxygenated around site 7 with some slight drops in oxygen, but not becoming too anoxic or hypoxic at all. So still fairly good oxygenation around Ashmead Channel. But now I'll talk about the nutrients. You will see it's a nice bell-shaped curve. So the ends of the channel again, fairly low in concentration, and then you have this peak around the wastewater treatment plant in site 2 of the system. And this is the same trend we picked up for the phosphates as well. So both ammonium and phosphate fairly high. So what was interesting in our study, we compared it to what Todd Switzer did his PhD a few years ago in Knysna. And when he did his work, what I would like to draw your attention to is just the scale. So phosphate DIP is fairly similar, but the ammonium, we're going up to about 160 micromoles in Ashmead Channel, where his highest was about 5.5 to 6 micromole. So a definite change. At this stage, it was about 15 years ago since he studied. And in that change, in that time, big changes had already occurred. For isotope results, so what I did was I went to the treatment plant and I asked them if I could collect a few samples, and they allowed me in. Collected these samples for Phragmites, Typha, in the wastewater treatment at the ponds, and we sent this material to UCT, and they did some isotope analysis for us. The results showed that the Phragmites and Typha was fairly high or enriched in nitrogen isotope. Then we also did the same thing around Ashmead for the Ulva, for the macroalgae that's blooming, as well as for Zostera capensis. So what's
what number plate?
What's generally found for isotope work, excuse me, I lost my train of thought. What's generally found is that signatures above 10 parts per thousand is normally considered a source from human or animal waste, and then signatures below that can be attributed to either natural processes or sometimes fertilizers and so on. But we can fairly say with confidence that the wastewater treatment plant has definitely been an influence or a contributing factor to the nutrients or the nitrogen in the system to the Ulva's growth. Then I'll just draw your attention over here. The Zostera was fairly low, but Zostera is a rooted macrophyte. So whereas Ulva is not, Ulva is drifting with the ebb and flow of the tide. So as the tide comes in, it will be distributed. So flushing of the heads, or the tide coming in through the heads is playing a role in maintaining a lower concentration in the rooted macrophyte Zostera capensis in that area. We also looked at redox potential, which is an indicator of how anoxic your sediment is. So in terms of sediment quality, at all our sites around Ashmead, the redox potential was fairly high or negative, going up to about 350 millivolts. That's what the sediment looked like. And then I compared this again to what Switzer did in his work, and he still had a positive value in Ashmead 15 years ago. But another big change. So the sediment is highly anoxic in the Ashmead at the moment. In terms of the benthic chamber deployments, so this is talking about what nutrients are coming out of the sediments and into the water column. So out of those anoxic sediments, don't worry too much again about the information. I'll just talk you through the important points. We've got the ammonium concentration on the y-axis and time over a 24-hour cycle. Both ammonium and phosphate are sources. There's an easier way to present this information. I'll show you in the next in my next chapter. But what's important to note here is that Switzer's work, again, if you're looking at the scale, is going up to about 12 micromole for ammonium. We're already starting at 60, going to 100. Phosphate fairly similar if you're looking at the scale, and nitrate being taken out of the sediment. So both ammonium and phosphate is becoming a source to the water column. So the flux is directed upwards, whereas nitrate is being directed downwards. Impact on the seagrass. I'm only going to talk about the seagrass to save some time. So we did some transect work looking at the percentage cover along these 5 transects. And if you look at past work that was done at these same exact transects, we've got Muir in 2000 and Jaden Schmidt's work in 2013. When we're just looking at the intertidal zone, Zostera capensis, the seagrass, we had 100% cover. But when we did our study in 2015, we see there was a huge impact on the Zostera. So what the macroalgae bloom does, it smothers the intertidal zone, and everything underneath there basically dies back. So what were our findings? We saw there was some low dissolved oxygen in the water column. When there's low dissolved oxygen, it encourages the release of ammonium and phosphate because of decomposition. When bacteria start breaking down organic material, they use the organics, they use the oxygen in their life process to break down the material, and then the result is the release of ammonium and phosphate, remineralization. And it's happening in this shallow mudflat areas in Ashmead Channel. So I just want to take you through a quote that was in Todd Switzer's work, in Allenson and Switzer's work. They said if either of these 2 features, dissolved oxygen and tidal flushing, should change, water column nutrients, ammonium and phosphate, would be expected to increase due to an increase in the flux of these nutrients from the sediments. Therefore, an increase in signs of eutrophication, examples, increased algal growth would ensue. So that's exactly what's happened. And when I spoke to Todd, he said he gave Ashmead about 20 years, and he said Prof. Allenson said he'd give Ashmead about 10 to 15 years before this would occur. And as usual, he told me Prof. Allenson was correct. So just in conclusion, we find that Ashmead is now a benthic driven system because of all the anoxic sediment it has. It encourages the release of ammonium and phosphates from the sediment. And as Ulva goes through its life cycle, it accumulates this nutrients, it grows, and when it dies back, it then becomes a source again. So it's a circle. And other studies have also found that Ulva can be a significant sink for nitrogen and phosphorus, storing up to 28 tons of nitrogen and 2 tons of phosphorus. So this is basically fertilizer sitting in this plant material. So what we found in our plant tissue, we had about a kilogram of nitrogen and phosphorus sitting in our plant material. So in terms of heavy metals, there weren't many. I've given an example of cadmium there. There weren't many metals, so the level of metal contamination in the plants weren't high at all. And we stated that because of these findings, it could be a potential. The algae could be a potential source of fertilizer or compost. The only way to get rid of the problem is really to reduce the nutrient input to the system, and this is actually a much bigger task. So fortunately, this big bloom didn't persist, as we have some of the other red tide species persisting in our other systems like sundays and swartkops. The phytoplankton, they occur all of the time. So the green tide in Knysna didn't persist. So this is a picture I took, I think about a year or 2 ago, and it's still present, but it's not as abundant. And there could be various reasons for this. What I suspect is that sometimes the wastewater treatment plant does fail, and when that happens, they pump a lot of chlorine out to sort of neutralize it or kill any bacteria that goes along with it. And this could have probably resulted in the dieback of the algae. But it does come up from time to time, but it's never been in at the scale at which it was in 2014, 2015. Okay, so this brings us to the next chapter, or our what we wanted to find. We want to find out, excuse me, is that we knew what was happening in Ashmead, but we wanted to get a picture of what was happening in the greater estuary, in particularly the sediments. So in terms of benthic flux research, at the time I was conducting this research, it was in parallel, Boyton et al. Were doing a global survey of research being done in the benthic realm across the world. And in their paper, their review paper, they told of the concern they had over the little data or the sparse data from the shallow waters of the Arctic, Antarctic, as well as Africa. And notably, Africa scored even lower than the Arctic. And the only research we could find, or I could find at that time in South Africa, was the previous work of Allinson and Howard Williams in Swartvlei, the Todd Switzer's work in Knysna, Birgit Cook in Swartkops, and then Snow and Taljaard's work in the East Kleinmonde estuary, and some of my work in the Great Brak estuary. So the aim of this study was basically to determine if there's a spatial difference in nutrient fluxes from the different regions in the Knysna estuary. So we do have a good idea of what the water column's nutrients is, but we don't have any idea. We didn't have any idea of what's coming from the sediment. How's the sediment? How's the biogeochemistry of the sediment influencing the system? So what we did was we deployed benthic chambers again over 24-hour cycle in these different regions in both summer and winter to get an idea of the spatial differences. And that's just a picture of the chamber. We had the chamber hooked up to a solar panel with a battery so that we could have power throughout the 24 hours. Okay, so this is the way that you can then present the data in terms of flux, and any bar going up indicates sediment acting as a source of nutrients is moving from the sediment into the water column, and any flux going down indicates a sediment removal or nitrogen being transformed. So what we found in all four regions, ammonium was really a source. This is flux on the y-axis and then time on the x-axis. So in all four regions, ammonium was acting as a source of nitrogen to the system, and this could be due to the presence of organic matter. The process of remineralization encourages ammonium to be released, and also the transformation of ammonium nitrogen into another species. So dissimilatory nitrate reduction to ammonium could also be occurring. So nitrogen transforming from nitrate into ammonium. For nitrate now, it was opposite. In all four regions, we discovered that nitrate was, the sediment was actually acting as a sink for nitrate. So it was being directed towards the sediment, or it was being removed out of the system. And this could be, once again, attributed to either dissimilatory nitrate reduction to ammonium, so it's transforming to another species of nitrogen, or it could just be due to denitrification. So nitrogen being removed via atmospheric pathway. In terms of the dissolved inorganic phosphorus, phosphorus was mostly also a source, but at times it was a sink, and the release, both ammonium and phosphate react in a similar way to organic matter decomposition. The inorganic form gets released, but removal could also be due to biological activity, burial, and absorption. Phosphorus likes to bind to sediments, and at certain pHs it binds strongly to sediments. So these could be the reasons why phosphate was being held or sort of acted as a sink. So in terms of our sediment characteristics for each of our regions, the upper estuary, lagoon, bay, and Ashmead, we measured organic content and sediment particle size. These two characteristics are very important to measure with your benthic fluxes where your changes are, because they influence what's happening to the nutrients. In terms of Ashmead, you can see there's a fair amount of salt and fine sands, whereas the upper estuary, lagoon, and bay have a more coarse and medium sand type of distribution. And this is mostly because it's a sandy system, because its catchment is basically part of the Brenton dune. In terms of organic content, Ashmead had exceptionally high organic content versus the other sections, and that's because of what we saw previously with the high anaerobic sediments and organic matter coming in from the wastewater treatment plant, etc. So what does this have to do with our results? We had a significant correlation for ammonium and phosphate with sediment organic content and silt. So these conditions favor the release of ammonium and phosphate. Okay, in conclusion, there's a spatial difference in the nutrient fluxes, most definitely. But what's important is that while the water column is oligotrophic, I didn't show this data, but we've got a long data set indicating the oligotrophic status of Knysna. And what do I mean by oligotrophic? Oligotrophic is a trophic state whereby you can view it as having little nutrients, and then mesotrophic is having a bit higher nutrients. Eutrophic is enriched, so over-enriched supply, like Ashmead Channel is eutrophic, so it's an over-enriched supply of nitrogen and phosphorus, and then hypereutrophic is like the worst you can get. So the nutrient flux from the sediment is actually high when you look at other systems from around the world. This is concerning because systems such as Chesapeake Bay in the USA, Weeks Bay, Alabama, Swan Canyon Estuary in Australia, and the Tagus. When you're looking at scale, Knysna Estuary is about 10 square kilometers. It's a microtidal system versus Chesapeake Bay and the Tagus Estuary. Chesapeake Bay is 11,000 square kilometers. The rate at which the fluxes are occurring are comparable to what's happening in these much bigger macrotidal systems. So what does this mean? It means that the sediments are already in a state where it can supply or drive the system from an oligotrophic state, which is a desirable state, into a more degraded state, perhaps a mesotrophic or eutrophic. So what happens is if the sediment's already in this state and more pressure in the catchment occurs, like more building or more population increases, means the little wastewater treatment plant can't cope, and whatever other catchment sources of nutrients comes into the system. If that continues, the trajectory of Knysna Estuary might change into a more degraded state. The water quality will become worse. So in terms of management, all this research, my research and other research that went along during this time, we presented this work to different stakeholders in a workshop. And we had representatives there from Sandbox. It actually was hosted at Sandbox, Knysna. Knysna municipality was there, Eden District municipality, some independent specialists, scientists and engineers, as well as NGOs were present. And the outcome was actually fairly good. They decided that they needed to look at the catchment, because the catchment is where the problem actually starts. So what's happening in the catchment is going to influence what the receiving water body, what happens in the estuary. And they would focus on the wastewater treatment plant. And I thought that was a good start. And in fact, after I heard several presentations in an estuary workshop about all the challenges facing estuaries and agencies, this workshop was actually not a good start. It was a brilliant start. The output from this workshop actually led to the local parliament. The research was presented at the local parliament, and there was a champion that was elected to deliver the workshop's results to the local parliament, and they actually funded a study. And there was a student from UCT Engineering that was looking at sustainable drainage systems to capture some of the pollutants coming into Knysna Estuary. So I'd just like to acknowledge my co-workers, Professor Janine Adams, Professor Brian Allenson, Professor Sam Talyard, Mr. Rian Witz. Marilyn was a student, Jessica Els was a student that helped with field work, and of course, South African National Parks. Thank you.
Thank you very much, Lucienne. It's fantastic to see and hear you talk through research with impact. So thank you very much for that. Thoroughly enjoyed it. I'm going to open the floor for questions. So if you have a question, put your hand up and I'll hand you over to the floor. Just going to have a look in the chat box as well. I've got a question from Sophisa. Sophisa, over to you. You are muted, Sophisa. You can go ahead.
Okay. Can you hear me now? Okay. I was going to ask, first, thank you for the presentation. I'm going to ask you if you consider doing any treatment studies, like your phytoremediation, not maybe only looking at the seagrasses, maybe also looking at things like your macrophytes, some types of macrophytes, maybe closer to the proximity of the wastewater treatment plant to reduce this nutrient loading, and also maybe further look into doing sort of toxicity studies, because you mentioned that there are harmful algal blooms that can grow in very larger quantities because of these nutrient loadings. And what happens to the plants after you have after harvesting? You mentioned that you use them as compost, but have you tested the plant for other toxins and things like that after being removed from the system or from the estuary? Thank you.
Okay, Sophie, so you've got two questions I'm gathering. So the first one was about the phytoremediation of the wastewater coming from wastewater treatment works before it gets to the system. Is that right?
Yes.
Okay, so there is in fact already a artificial wetland that's naturally occurring. It's a bed of Phragmites that occurs along the banks of the estuary, and the wastewater treatment plant's outflow actually moves through that bed before it gets into the Bongani Inlet. but it's too small to cope with the load coming through. So not everything will be captured. So that's why we still have an impact on the system.
Okay.
Getting some feedback there. I don't know if it's on my laptop.
And then any toxin study?
Your second question was about what was it about the composting? So the second question was about other pollutants. We did in fact just measure metals in the algae, and this was merely a suggestion. It would be, it's out of my scope of research to determine, how effective this can be. It's a recommendation. It was put forward, but I mean, it wasn't taken up. So the algae is not being harvested. And I think also because it's not occurring in such a high abundance again, that it hasn't been harvested. So the nutrients are not removed in essence by removing the ulva. Does that make sense?
Yes, thank you.
You must just let me know if you need further clarification or if I've missed your question.
No, I was just asking about, since you mentioned that you have done some, I was certainly interested in the toxin studies. You said you have you have done some heavy metals removal using the artificial wetland that is on site. So I think that's what I wanted to know, if you're doing any treatment studies. So I think that answers my question.
Okay.
Yeah, thanks.
Thank you, Sophie. So any other questions before I go to the chats? Okay, I'll in the meantime just go to the chat. There's a question by Vainan C. I'm assuming it's Vainan Carlitz from Eric Lansnode. He says, "Hi Lucienne, thank you for a great talk. Did you at all compare your isotope nutrient work on the vegetation of the channel to that of the upper estuary catchment to determine the influence from agriculture or other anthropogenic activities? I'm assuming the meander can act as a collection site for a lot of sediments. The sediment and nutrients, particularly following high rainfall, is currently seen along the Southern Cape."
Yeah, so let me just get your question correct. You want to know if I did a comparison between, if I collected first of all, and the answer is no, we were just focused on Ashmead at that time. But I suppose we would be able to pick up past work I did in East Kleinamond, actually. We looked at a range of isotope signals in Phragmites from the head of the estuary to the mouth. And we picked up different sources. So we could pick up at site 1, at the mouth of the estuary, there's quite a few houses that are on septic tanks. And then further up, it's more natural vegetation and whatnot. And we had actual gradient going from natural signatures all the way to septic tank signatures. So it was like from 4 all the way to 21 where the septic tanks were. But no, we didn't do it in this study. And then I'm sorry, what's the second part of the question?
Let me just have a look here. I'm assuming the meander can act as a collection site for a lot of sediment and nutrients, particularly following high rainfall as currently seen along the Southern Cape.
The meander, meaning the Ashmead. Does that? I suppose that's what you mean. Yes, it is actually, and that's why they. Some of there was a hydrologist as well in that workshop, and they were talking about this exact topic, and that's why it was decided to do a catchment type of study to sort of catch everything before it comes down. I think the results of that study might be out already. I'm not sure if the student has graduated yet, but yeah, it is definitely a connection point.
Lucienne, I've got another one for you. What measures are in place to reduce the nutrients in the wastewater being discharged to the estuary?
Okay, so good question. this after the workshop all as well, Knysna was in the process of upgrading the treatment work facilities. But I mean, like all of our wastewater treatment plants in the country, it's currently we need specialized skills, and we need the effluent to be treated to a much better standard. There's numerous cases in the country where the wastewater treatment plants are not up to standard. So it's a bigger societal issue.
Thanks, Lucienne. Any other questions? Okay, none from the participants. Maybe I can ask one, Lucienne. Lessons learned from engaging with management and decision makers on research results?
Yeah, look, I mean, the first thing is you got to have them on your side. Your relationships are key. It took me a while to form relationships with different stakeholders in Sandbox and like municipalities and so on. But the turnover of staff is also a problem. So when new staff come in, like what happened now actually at Sandbox this year, the head senior ranger is left. The one above, Megan is left to a new post. So it takes then a while to build that relationship again. I would say lessons learned is really just trying to be on good terms with these guys and getting them involved in what you're doing. And once you have their buy-in, things tend to go a bit smoother. They're more open to receive, your research or whatever findings. And afterwards, they actually come and ask for help. So that's good. That's what I've learned.
Thank you, Lucienne. Thank you very much. All right. I think I'm going to close the question sessions and just conclude with two announcements. One is that this session will be posted on the SAEON YouTube channel. So please go have a look at that, as well as all of the previous presentations in this series. And then the second one is our next presentation will be on the 2nd of November, and it will be by Professor Sarah Berry, an assistant professor at MIT, US, working on machine learning with a focus on environmental sciences. Should be very interesting, and I hope to see all of you there. Thank you, Lucienne. Thank you all for attending. Yeah, have a good day. Cheers.
Thanks, Sean. Cheers. Bye-bye.